Okay, so let's just take a look and see how we can use tree diagrams and how they're related to our probability statements that we've been looking at. The better you get at tree diagrams, honestly, the easier a lot of questions will be to answer. So sort of get used to them, understanding them, and if you're honestly ever not sure where to start in a probability question, I would start with a tree diagram. So the Pew Internet and American Life Projects finds that 93% of teenagers use the internet, and 55% of online teens have posted on a social networking site. Now, this is a conditional probability because the condition here is that 55% of the online teens, so the condition was that they were already teenagers that were online. We want to know what percent of teens are online and have posted a profile. Honestly, you could probably do this without using a tree diagram, but I just want to show you what it looks like so that as you come across questions like this, they get a little bit easier. So we have two things going on right now. We have teenagers using the internet. The complement to that would be not using the internet. 55% of those have posted a profile. The complement of that would be not posting a profile. So two things we're looking at: internet, not internet; online profile, not online profile. So let's see what that tree diagram looks like. Number one, we have our first randomly selecting a teenager. 93% are online, 7% are not online. So when we add these branches together, they add up to 1 because 100% of the teenagers are either online or they're not. Now, let's take a look at where we put that 55%. That 55% deals with them being on a social networking site. So we know, based on the condition that they were online, 55% of them have an online profile. What's the opposite? 45% would not. Notice that branch adds up to 1 because profile, no profile add up. That's all the teenagers that are online. If they don't use the internet, then obviously 0% are going to have an online profile, and 100% are not going to have an online profile because they're not even online. So let's see what that probability looks like. The probability that they're online is 93%. We're given this conditional probability. The probability that they have a profile given that they were online is 55%. So we know in order to answer my and question, online and have a profile, I need the probability that they're online times the probability that they have a profile given that they are online. And that's what my tree diagram allows us to do. So I just can multiply my two answers together to get 51.15%. You need to show this multiplication here. And the nice thing about a tree diagram is honestly you can always multiply the branches out to get the end of the branches, and that will help you a lot once we get to more difficult questions. All right, so the next couple slides, we're just going to go over some questions on independence, when to use tree diagrams, multiplication rule, and your conditional probability. All right, so go ahead and take a minute and try this one on your own. Hopefully, after everything we've done, you should be okay with this one. Go ahead, take a minute, pause, and then I'll just briefly explain the answers. Okay, a couple things I just wanted you to note. Number one, notice how we've defined A and F. So if you're going to use A and F, or use symbols instead of writing out the answers, you need to define what they are. So A, if they have allergies; F is that they have female. So find the probability of A. Notice A, we've defined it to be allergies. Don't just write the probability of A without defining A. Remember, you want to show your fraction and your decimal answer. So hopefully you looked at this and you said, you did something wrong. What did I do wrong? I didn't find the totals. Always find those totals first. Makes it much easier. So we're going to find A given F and F given A. So allergies, given that they're female, is we are just now looking at the female column, so total of 23, 10 of those. Females, given that they have allergies, is we're just now looking at the allergies column with a total of 18 and 10 of those females. So just keep this in mind, this 0.343. We're going to take a look at how we can use this to help prove whether or not allergies and females are independent. All right, so we want to know, are the events A and F independent? Are the fact that they have allergies and being female independent? Well, on a previous slide, we learned that if the probability of the event occurring, the probability of them having allergies, is equal to the conditional probability, then we know that the two events are independent, okay? So that's basically like saying if you have allergies, being a female is not going to affect whether or not you have allergies. So a couple of things that you're going to want to show. One is you need to show this probability statement right here. The second thing you need to show is the actual probabilities of those two. Don't just state equal, not equal, independent, not independent. You need to show. Well, we know that the probability of getting allergies was 18 out of the 40, so that was 45%. Allergies, given the fact that they were female from the previous slide, was 0.434. So those two probabilities are not equal. So being a female does affect the probability of having allergies. Allergies is 45%, but females have a lower percentage of allergies, so maybe being a female makes you have less allergies. Therefore, they're not independent. All right, so oftentimes students will say, how do I know when to use a tree diagram versus a two-way table? Okay, here's an easy way to sort of tell. Anytime you're given conditional probability, you always want to have a tree diagram. So knowing that they were online users, what was the probability they had a social networking profile? So that was a conditional probability. So oftentimes it's easier to use a tree diagram. Get used to tree diagrams, get practice with them, they'll be so much easier. If you're given counts, so you're saying like a certain number of people in this category, that's when you're going to use a table. All right, so let's go ahead and take a look at this one. January 2010, the Kaiser Family Foundation released a study about the influence of media in young people's lives. So you want to be able to recognize sort of what your trees are going to be in your tree diagram. I guess your branches in your tree diagram. So here's what we know. 17% were classified as light media users, 62% were moderate, and 21% were classified as heavy media users. So basically one of your branches is going to be the classification of how much they use the internet. So of the light users, 74% said their grades were good, 68% said their grades were good, and 52% said their grades were good of heavy internet users. According to the study, what percentage of young people describe their grades as good? Now, how do you know you want to use a tree diagram for this? Here's how you know. Because it says, of the light users that responded, that was a condition. The condition was the light users, 74% described their grades as good. Of the users that were moderate users, 68% described their grades as good. So this is telling you, A, what your first branch is. Your first branch is going to be the classification of the media users. Why? Because that's what you're sort of given first. Then you're given the percentage of their grades. So let's take a look at what this tree diagram looks like. Number one, our first branch is going to be, and this is a little bit different than the previous one, but that's okay. The first branch was our light, medium, and heavy. Now, we know that 74% of light media users had good grades. Well, remember that these branches always have to add up to 1. So think about it as a complement. Good grades, not good grades. So 26%, 1 minus 0.74 gives me my 26%, has to add up to 1. Medium users, they said 68% were good grades. So not good grades would be 100 minus that, or 32%. Heavy internet users said 52% had good grades. Subtract that from 100, so 48% had good grades. All right, now what are these little things at the end here? These are all of your and probabilities. So this is light internet and good grades. Light internet and not good grades. Medium and good grades. Medium and not good grades. Now here's the tricky part. What percent of young people describe their grades as good? You can't just add up these probabilities, 74, 68, and 52, because that was based on the condition that they were light, medium, or heavy internet users. So this probability right here, this 0.125, is light and good grades. This 0.4126 is medium and good grades. This 0.1902 is heavy and good grades. So notice there are three sets of internet users that describe their grades as good. This would be very difficult to do if you did not have that tree diagram. Because how can I answer this question? Now that I have this tree diagram, it's easy. Okay, because all I'm going to do is say good grades, add that first one up. Good grades, add it to the second one. Good grades, add it to the third one to get 65.66% of young people describe their grades as good from the three various categories. If you don't have this tree diagram, it's difficult to do. And the other thing I wanted you to make sure you know is that these branches add up to 1. Each of these individual branches add up to 1. And this should all add up to 1. If it doesn't, that means you did one of the probabilities incorrectly. Okay, let's take a look at this one. This one's a little bit trickier. And this is where the tree diagram comes into use and is so much easier than you trying to figure this out without a tree diagram. I think it's very difficult, almost impossible to do. So what percent of students with good grades are heavy users of media? Well, hopefully you look at that and say, okay, well that's a condition, but how do I know what the condition is, what was imposed upon it? You want to read this and say, what percent of students with good grades? That's what you're given first. You know that they have good grades, so that is your condition. Are heavy users of media. So whatever is kind of after the word are, that's sort of like asking the question, and that's not your condition, it's what's before the condition. So when I write out this conditional probability, the probability that they're heavy internet users given that they have good grades. Now, I'm going to use my formula, heavy and good grades. That's easy. Boom, I just go right over here, plug that down there. Now notice the bottom is the probability that they get good grades. You can't just use that 0.52 because there are 3 places where they get good grades. You have to add up all 3 of those places in your denominator. Without the tree diagram, once again, super hard to find. You want to make sure you show this fraction right here and then your final answer, 0.166. So we know about 17 or 16.6% of young people who say they've had good grades are heavy users of media. All right, so go ahead and take a minute and try this one also. This one, go ahead and read it, and then I'll go over the explanation in a second. So go ahead and hit pause if you want to read it. Okay, so when you're reading this question, the question is asking, what is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance? Why didn't we need to draw a tree diagram? Well, the reason here is because they're all independent events, and there's no condition being imposed on it. It's just basically saying, like, what's the probability that if we have 9 innings in a row that we get no hitters? Each of those events are independent. Each of those events are independent, so we can use our multiplication rule to get that answer. So what's the probability that we have no hitters for 9 innings? I can just multiply the probability, since they're independent, of each of the 9 innings being no hitters, which is 0.4. Okay? So what work do you need to show? You literally just need to show this 0.4 to the 9th and then your final answer. All right, so let's look at one of these at least questions where we're subtracting from 1. So the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, 5% of normal pregnancies will result in a positive test. Among 100 women with normal pregnancies, what is the probability that at least one will have a false positive? Okay, so this is basically like saying the probability that 5% of normal pregnancies will result in a positive test. So this is like saying the probability that you're going to get a positive result given that you have a normal pregnancy is 5%. So it's going to say there's an abnormality even though there isn't. Okay? Now, we can find the other probability. So 5% of the time you're going to get a positive with a normal pregnancy. What's the other 95% represent? The other 95% of positives are going to be if there was actually an abnormality. So you want to figure out both of those probabilities. So you're getting a positive, it's normal is 5%. Getting a positive and it's abnormal is 95% of the time. So you have 5% of the time where it's incorrect, basically, and 95% of the time that it is correct. So the question says, what's the probability that you have at least one false positive? So this right here is your false positive. So that would mean if you have at least one false positive, you have 1 through 100. Okay, that can be difficult to do. So instead of doing at least one false positive, let's do the complement and do 1 minus the probability that there's no false positives. So that is saying if I take 100% minus the 0.95 represents the false positives for all 100 of them, that gives me 0.994. So I'm taking out no false